The purpose of this video is a very brief history of life on Earth, essentially to set the stage for the beginning of some of the chemical changes necessary for biology to even start on Earth. So we're starting back here about 4.5 billion years ago with the formation of the Earth. And this process was called accretion. Accretion is simply just the processes that allowed the Earth to form the global mass that we know now. There was no atmosphere. The surface was liquid, but mostly molten rock. Lots of volcanism. Lots of effects from the sun. Lots of comets hitting the Earth, and you can see it's in these artist renderings, it was a pretty nasty place to be. Over time, Earth cooled and began to solidify, such that a liquid core still remains, but the crust developed as a result of this cooling. Because the core is full of metals, that's why we have GPS today. That's why we have magnetic north. It's because of this molten metal-ridden core. Additionally, the moon created tides because of the fact that as the Earth cooled, liquid water could form and condense because the early beginnings of the atmosphere were happening. The atmosphere was generated not only from the cooling of metals and molten rock, but also from the preponderance of volcanoes. So volcanoes were emitting a lot of carbon dioxide and methane and sulfur and water vapor into the atmosphere, creating a very rudimentary atmosphere. And once the atmosphere was there, more water could form and the oceans could form. So it created a positive feedback loop to allow a more hospitable environment now that there was an atmosphere to protect the Earth from a lot of the comets and other sorts of extraterrestrial things hitting Earth. And I'm not talking about aliens, I'm talking about comets and solar winds and other things like that, just to be clear. So this figure here is looking at the change in the Earth's atmosphere over time from when it was roughly developed about 4.4 billion years ago to now. Several things you should note. First, oxygen does not appear in the Earth's atmosphere until roughly 2.5 billion years ago. We'll talk about why and how later, but you'll notice at the beginning of the Earth's atmosphere, when we have evidence for, it was mostly methane, ammonia, nitrogen, water vapor, and carbon dioxide. This is going to be important when we talk about the beginnings of chemical changes for life on Earth. But you can see that for most of the Earth's history, nitrogen is the key gas in the atmosphere. It was switched out for other things, but only recently, meaning 2.5 billion years, did oxygen become important. So that's great and all, but how do we know this? There are several ways. First of all, ice cores. If you go to Greenland or Antarctica or other places with large ice sheets and drill deep enough, you get changes in ice composition over time. Ice is still liquid water, but inside are these bubbles. Inside the bubbles are the gas of the atmosphere at the time it was formed. So gas bubbles created today with the freezing of ice would contain CO2 and methane and water vapor and nitrogen. But in the early Earth, if you go far enough down in an ice core and analyze these gas bubbles, it can tell you which gases were present over time. So you can almost imagine an ice core laying on its side. The bottom of the ice core is older, the top of the ice core is newer. The other bit are geologic formations like this rock here. You can see these bands. These bands are created because the Earth's atmosphere is what we call reducing. You can think of this as rust formation. So it had a reducing atmosphere. There was not oxygen present in it, at least in O2 form. So therefore, a lot of chemical reactions could occur in the absence of oxygen. Also keep in mind, as this atmosphere was developing, the oceans were present and starting to form, which leads us to the next part of this section coming up: chemical evolution, biochemical evolution, and then the beginning of life